Alrighty, I've been playing around here this evening with my circuit boards here and things, and I've been working on a pulse width modulation with torque control, and doing some experimenting here, doing it all out of transistors, out of discrete components, except for the opto isolator here. That's the only thing that's IC, but everything else is discrete components. And this is the circuit that I came up with here, playing around here with this, and I'll do a little. First of all, I will show a demonstration how this here works. I have a small DC motor here with a piece of tape on there to show that it's spinning. And what this is going to do is, whenever I put a load on the motor here, I'm going to be able to watch my oscilloscope here, and I'll be able to watch the waveform. Whenever I put a load on that motor, this waveform the pulse width should expand until it gets to a full line on top here. And that would be full DC voltage. Right now it's on half the time, off half the time, so it's about 50% duty cycle. I'm using my audio generator here to generate a signal into the circuit. I have a voltage reading across with this here one here and this here, and I'll explain that in a second also. But let's just take a look at this here now. When I put a load on this motor here, right here, like this here is an indicating light on right here. That light will start coming on. When that light comes on, that's indicating that a load is being put on the motor. It's also indicating that it's sending a signal through a feedback network that will cause the motor voltage to increase due to the width of the pulse here. So now I'm going to put a load on the motor now and watch the pulse on there. It keeps on getting larger and larger as I put the load on harder. Now it's at full voltage. And it's hard to stop this motor. Now this here meter here, that is the voltage that is dropped across this here resistor right here that turns on the opto isolator. This meter right here is the voltage drop across the feedback transistor, which is right here. This 200 ohm resistor right here builds up a voltage across there, and that meter is hooked there to monitor the voltage that's being inputted back to this front of the circuit. I'll explain how this works now. Okay, the explanation of how this works now. This area right here, this part of the circuitry right here, that is all a Schmitt trigger circuit, which takes a sinusoidal sine wave here, around 10 kilohertz, and then it converts that sine wave into a pulsating square wave on the output here. That square wave then is fed into this here MOSFET, which is an IRF 630. That MOSFET is biased on here, so that whenever this here square wave comes through here on a positive pulse, it pulses the MOSFET into conduction, where there's a very small voltage drop across there, and most of the voltage being dropped across the motor. And through that there pulse width modulation going on here, the MOSFET is running the motor through these pulses. This 5 ohm resistor here, that is there as a sense resistor. When the motor begins to stall, that will sense a current flow through there, increase, and will develop a voltage. Now, under normal running conditions, all of this circuitry is pretty much out of the circuitry, out of the rest of the circuit. It's pretty much just running idle and not really having any effect too much at all on any feedback. However, when I put a load on the motor, when that load goes on the motor, that motor resistance goes down, current flow begins to increase through here, negative current, we're going with electron current right now. It builds up a voltage across this 5 ohm resistor, and some of that negative current now is flowing into this PNP transistor. The PNP transistor then allows conventional positive flow into the LED and the opto isolator, and now this here transistor is biased on enough to put it in a linear region so that any variance in motor resistance will immediately cause this transistor to conduct off or on harder or off less. In other words, if it's not working as a switch. If it's working as a switch, then it would have to wait until I get enough voltage drop between the base and emitter dropped across there to turn it on. I don't want that to work as a switch. I want it to work in a linear mode. So since that's biased on to this self-bias right here, collector feedback here to the base, 47 kilo ohm resistor, it's already biased on enough that there's just enough current flowing through here to light this LED and to keep this here transistor operating at a linear region also. So that's why this LED is on very dimly, but if there's enough current flowing through there to produce enough voltage at the base of this transistor here to keep that in a linear mode. So that being in linear mode also, now its output is fed back over to here, keeping everything tied together here, but at a very low signal voltage, very low, because it's only at idle. As I said, now the motor gets a stall on it. The increase in current causes the voltage to be dropped across here greater. That negative current flowing into this PNP transistor causes this PNP transistor to conduct harder, causing this here now to turn on harder in the opto isolator. With that being turned on harder, now we have a more positive flow through this transistor here, the LED lighting up brighter. That positive current now flowing through here also allows this here ground from this transistor to become more conductive now. It causes a negative current to flow through it, and that negative current now flows in the base of this PNP transistor, which then causes a positive signal flow, a greater positive signal flow now to be fed back over into this area here, which causes now the Schmitt trigger circuit to come on harder. As it comes on harder, the pulse width begins to increase. So as long as there is a load on this motor, and that load gets stronger and stronger until the motor goes into a stall, all of this circuitry here turns on harder, sending a signal back over to here, causing this to increase greater until it's complete DC voltage coming out of this here, causing the MOSFET to be on with no more pulses but pure DC going through the motor. And that's how the feedback works. This here potentiometer here allows me to adjust the speed of the motor by adjusting the pulse width by the amount of allowing this here sinusoidal wave to come in here. As I adjust this base voltage here, that allows the Schmitt trigger to trigger on at a lower voltage, peak voltage on this 10 kilohertz signal. So that right there is the motor control, manual control, and then all of this here is the automatic control, which feeds back current back into here, voltage back in here, and current back in here to cause an increase in pulse width. Without any of this, there would be no feedback, and the pulse width would not increase with the load on the motor. But by putting all this in here, allows the pulse width to increase with respect to the load that's put on the motor, because everything is run in a linear fashion. These are all running linear. And that's pretty much how this circuit works. I put a load on the motor, the light comes on, and the pulse width increases till it goes to a steady DC. I can put a light load on the motor, and I can put a heavy load in the motor and back to a light. Because everything's running linear, I can also put a load on the motor in a linear way as well, and then get a feedback linear as well. Now it's pure DC. And there again, it also depends on the frequency that's set to run the motor too. I put a different motor in there, and I have to change the frequency to match the motor, and that's just done experimentally. Okay, well that's what I want to share here on this here adventure here on designing a pulse width modulation with torque feedback. And this was an experiment to see how it worked, and I really enjoyed playing around with this here, and just wanted to share that to give a little insight of how this works. Okay, thanks for watching. Bye.